So what happens when the auxiliary equation has a repeated real root r? Or said differently, what happens when the discriminant is 0? One can prove the following result by substitution. If the auxiliary equation has one repeated real root r, then y of t equals c1 e to the power rt plus c2 t e to the power rt is the general solution to the differential equation. So what we have to note here is that an extra t shows up here. An extra factor of t. So let's see how that works with an example. So you want to solve the initial value problem y double prime plus 4y prime plus 4y equals 0 with initial conditions y at 0 equals 1 and y prime at 0 equals 3. So we go to the auxiliary equation first. And so we replace the y double prime by an r squared plus 4 times the y prime becomes an r, and then plus 4 as a constant term, that equals 0. To solve that, we have to look for a sum of 4 and a product of 4. And so we can factor that as r plus 2 times r plus 2 equals 0. And we see that that is a repeated root. It shows up twice. And so we only have one root here, namely r equals -2, but it's a root with multiplicity 2. Or stated otherwise, this is a repeated root. So now our general solution is as follows. We're going to have y of t equals c1 times e to the power rt, and in this case it's -2t. So we have e to the power -2t, and then we're going to repeat that one more time, but we're going to add a factor of t. Right, so we're putting in a t here, and then we're going to repeat the e to the power -2t. Okay, so that's our y of t. We'll also need to know what y prime of t is to figure out what the values of c1 and c2 are. So if we're looking at y prime of t, then that's equal to -2c1 e to the power -2t. And then here we'll have to use a product rule. So we take the derivative of t, which is 1. So I get plus c1 e to the power -2t. And I don't need to put that one here, but I want to make it clear that this comes from a product rule. And then we add the -2 c2 t e to the power negative 2t, right? We take the derivative of the second one, and that gives us that negative 2 here. So you just write that here, that this is a product rule. And now we can take a look at the initial conditions. So the first initial condition, we have y of 0 equals 1. And so that leads to 1 equals, plug in 0 here. So we have c1 e to the power negative 2 times 0 plus c2 times 0, right? That is our t here. And then e to the power negative 2 to the power 0. And this second term completely disappears. This is just c1. And so we get c1 basically for free here without having to solve a system of equations. So the second initial condition is y prime at 0 equals 3. So that means that 3 equals, and now let's plug in 0 here. So that's negative 2 c1 e to the power negative 2 times 0 plus c2 times e to the power negative 2 times 0, and then minus, and then minus 2 times c2 times 0 times e to the power negative 2 times 0. And it gives us 3 equals negative 2 c1 plus c2, and then this is 0. We know that c1 is 1. So I put in 3 equals negative 2 times 1. We got that from here. Plus c2. And then bring this to the other side, and we get 5 equals c2. And so our final solution for our differential equation, our initial value problem, is y of t equals c1 times e to the power negative 2t. c1 was 1, so that's e to the power negative 2t. And then plus c2, which is 5. So that's plus 5t e to the power negative 2t. And that's our solution to the differential equation. And now, in general, we can now state that when we look at our homogeneous second order differential equation with constant coefficients, then for any real numbers a not equal to 0, b, c, t naught, capital Y naught, and capital Y1, there exists a unique solution to the initial value problem. A y double prime plus b y prime plus cy equals 0, with initial condition y at t0 equals y naught, and y prime of t naught equals y1. The solution is valid for all t in negative infinity to infinity. Now, we haven't quite shown everything here yet, because we haven't done the complex case yet, but we will see that this is true for any real numbers a, b, and c in our differential equation.